Welcome to the solutions to the Regents Physics Current Electricity problem set, problems number 27 through 30. Number 27, a 20 ohm lamp and a 5 ohm lamp are connected in series and placed across a potential difference of 50 volts. What is? So they gave us the two individual resistances and they gave us the voltage in the circuit. The equivalent resistance in the circuit, the current in the circuit, the voltage drop across each lamp, and the power dissipated in each lamp. All right, the total resistance is easy enough. It's the sum of the resistors in the circuit. So that would be the 20 ohms plus the 5 ohms for a total resistance of 25 ohms. This technically should be a 25 with a decimal point after it without the 0 to the appropriate number of sig figs. The current in the circuit, well, that's the total current they're referring to. In order to calculate any total quantity, you have to use other total quantities. So that would be total voltage of 50 volts divided by total resistance, which we just calculated was 25 ohms. And this will give us a total current in the circuit of 2 amps. The voltage drop across each lamp would be the voltage, how much of the total voltage is used up by each lamp. This is a quick V equals I times R calculation for each lamp. So for our first one, 2 amps, being a series circuit, they all get 2 amps. Current remains constant. So 2 amps times 20 ohms and 40 volts. For the 5 ohm lamp, 2 amps times 5 ohms is 10 volts. A nice check, by the way, is when you're done, add your voltages together. It should be the total that you have in the circuit altogether, and indeed it checks. That's a nice thing about current electricity. If you're willing to take the time to do so, you can always check and make sure that your answers all add up and make sense. Okay, and lastly, the power dissipated in each lamp. Power is in any number of ways, but in this case it makes sense to use voltage and current. You could actually use V squared over R, or you could use I squared times R. Usually people choose this one because it's the easiest one. So 20 ohm lamp uses 40 volts and 2 amps. 40 times 2 is 80 watts. The 5 ohm lamp uses 10 volts, also gets 2 amps. 10 times 2 is 20 watts. What this says to you is that the 20 ohm lamp is 4 times brighter than the 5 ohm lamp because, of course, wattage is an indication of a bulb's brightness. Okay? And you probably already knew that before you even took the course. All right, on to 28. The load across a battery of 2 resistors with values of 15 and 45 ohms connected in series. What is the total resistance of the load, and what is the terminal voltage of the battery if the current in the circuit is 0.10 amps? Well, total resistance, again, they're connected in series, so you just add them together. 15 ohms plus 45 ohms is 60 ohms of total resistance. The terminal voltage we calculate by V equals I times R. This would be the total voltage supplied to external resistances. And so I was given as 0.10 amps right here. And our total resistance was 60 ohms from part A. And a tenth of 60 is, of course, 6.0 volts. 29. A lamp having a resistance of 10 ohms is connected across a 15-volt battery. What's the current through the lamp? And then what resistance must be connected in series with the lamp to reduce the current to half an amp? Let's start with A. I equals V divided by R. 15 volts divided by 10 ohms gives us 1.5 amps. All right, now they want to connect another resistor in series with the lamp. And if you take a look, it's the same equation, except in the denominator, for total resistance, where we recognize that it's the sum of the resistance we're adding in series to the one we already had. So this is still the total resistance, and in series, that means you add them. Okay? And they want that that current to be 0.50 amperes. Well, in order to do this, we then multiply both sides by R plus 10. That would give us 0.5 times R plus 0.5 times 10, which is 5, equals 15. Subtract 5 from both sides, and that would be 10 on the right-hand side. And divide both sides by 0.5, and this would give us a resistance value of 20 ohms. Okay? If you don't understand this problem, make sure you ask in class tomorrow. And lastly, we have a string of 18 identical holiday tree lights connected in series to a 120 volt source. The string uses 64 watts of power. The key to this question is that the lights are identical. That means, what does that mean in electricity talk? It means they all have the same resistance. Our voltage source is 120 volts. That's the wall voltage as you plug it in. And it tells you that the total power for the entire string is 64 watts. They want to know the equivalent resistance of the light string. Well, what you have here is the total voltage, and you have the total power. So by using those two, you could find the total resistance. P equals V squared over R. So R would be V squared over P. 120 squared over 64, 225 ohms of total resistance by all 18 lights. What then would be the resistance of a single light? Well, if they're identical, and that means they all have the same resistance, then all we need to do is take the 225 ohms, divide by 18, and that would give us the resistance of one lamp. So 225 divided by 18. Each lamp has 12.5 ohms of resistance. What's the power dissipated by each lamp? To do that, again, same thing. If the total power for all the bulbs is 64 watts, then the power for one bulb, connected in series that is, would be just to take them and divide by 18 of them. So each bulb has a brightness of power of 3.56 watts. All right, that'll do it on our solutions to 27 through 30. More to come. If you have any questions on any of these, ask in class tomorrow, and we'll also do problem 31 in class together tomorrow.